In the vast expanse of space, scientists have detected a radio signal from a star system known as YZ Ceti, located 12 light-years away. This signal carries a potential signature of a magnetic field similar to our planet's, possibly indicating a rocky exoplanet orbiting YZ Ceti. This discovery raises questions about the similarities between distant worlds and our own, as well as the search for life beyond our solar system. Radio signals, which travel at the speed of light, provide valuable information about stars, planets, and the universe's origins. Detecting these signals relies on radio technology. Astronomy radio telescopes, like the Very Large Array in New Mexico and the now-defunct Arecibo Observatory in Puerto Rico, detect and analyze radio signals from space. They provide valuable information about the universe. Radio signals from satellites have practical applications in GPS navigation, weather forecasting, and Earth observation. These signals play a significant role in our modern technological infrastructure. The star system YZ Ceti, located 12 light-years away, contains at least 3 known exoplanets, including YZ Ceti b, a rocky, Earth-sized planet in close orbit around its parent star. Days recently, using the Very Large Array, scientists at Bucknell University, Professor Jackie Willitson and her colleague J. Sebastian Panetta, detected a repeating radio signal from YZ Ceti. The signal, recorded at a frequency of 2 to 4 GHz, appears to be modulated by the rotation of the star and the orbit of YZ-CB. This suggests an interaction between the star and the planet's magnetic field. This discovery has significant implications for understanding exoplanets and their magnetic fields. While YZ-CB is unlikely to support life due to its proximity to its star, the detection of its magnetic field provides a method for discovering more habitable worlds in the future. Magnetic fields are a fundamental force of nature, guiding compasses, aiding bird migration, and shielding our planet from solar wind. They also play a role beyond Earth. Our Sun possesses a complex and dynamic magnetic field that influences its activity, from the formation of sunspots to solar flares. Magnetic fields shape the structure of galaxies, directing interstellar gas movement and influencing star formation. Importantly, magnetic fields in space may impact planetary environments and the potential for life. A strong magnetic field can protect a planet from harmful radiation from its star, helping to maintain a stable atmosphere and potentially favorable conditions for life. That's why it's so interesting to detect a potential magnetic field on exoplanet YZ-B. This discovery could provide valuable information about the planet's atmosphere and its potential to support life. But how do magnetic fields affect the detection and interpretation of signals from space? To understand this, we need to delve deeper into the nature of radio signals and magnetic fields. Radio signals, as electromagnetic waves, consist of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter as they travel through space. When a radio signal passes through a magnetic field, it can undergo different changes. Its direction can be deflected, its polarization, orientation of its electric field, can be rotated, and its frequency, number of waves passing through a point in a given time, can be shifted. These changes can provide valuable information about the magnetic field that caused them. By studying these changes, scientists can infer properties of the magnetic field, such as its strength and orientation. However, magnetic fields also present challenges for detecting signals from space. They can cause interference, making it difficult to detect the signal, and can distort the signal, making it hard to interpret. This is why the study of magnetic fields is crucial in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information that may be hidden in the signals from space. To better understand the influence of magnetic fields in creating favorable conditions for life on a planet, let's turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard, Mars. The red planet has long captured our imagination with its towering volcanoes, deep canyons, and hints of liquid water. It is one of the most intriguing places in our solar system. However, Mars also presents us with a mystery. Unlike Earth, Mars has a very weak and inhomogeneous magnetic field. This has serious implications for the planet's atmosphere and its ability to support life. Mars' magnetic field is not created by a dynamo in its core, like Earth's. Instead, it is the remnants of magnetism trapped in the planet's crust from when Mars actually had a global magnetic field. Without a strong magnetic field protecting it, Mars' atmosphere is directly exposed to the solar wind, a stream of charged particles emitted by the Sun. Moreover, new models presented by R. Sakata of the University of Tokyo and others suggest that a weak magnetic field, like Mars after its dynamo has turned off, could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, around 6 times faster than without a magnetic field. The reason is that the weak magnetic field strength lines are easily repelled by the solar wind, creating a path for ions to escape into space over the night side of Mars. This suggests that Mars' remaining magnetic field may have hastened the planet's transformation into the cold and barren world it is today. Over billions of years, this caused Mars to lose much of its atmosphere, a process known as atmospheric stripping. It turned Mars from a potentially warm and wet world in its early history into the cold and dry planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can lose the things that make it habitable: atmosphere and water. By the way, we've already looked at the problems and potential solutions to make Mars a second home for humanity in a separate analysis. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research, with more than 1,000 discovered to date. They offer a wealth of opportunities to learn about the diversity of the planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. It was discovered on a Neptune-sized planet called HP 111 bits. HP 111 bits is located about 123 light-years away in the constellation of Swan. It is a hot Neptune, a type of exoplanet that's similar in size to Neptune, but much closer to its star, resulting in high temperatures on the planet's surface. The detection of a magnetic field on HP 111 bits was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure, atmospheric properties, and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life. That brings us back to YZCTB, an exoplanet from which a signal was recently detected. If this signal is indeed indicative of a magnetic field, it can have a major implication for our understanding of this exoplanet and its potential for life. Traveling through space from the familiar landscapes of Mars to the far reaches of YZ Ceti, we've truly come to realize the invisible power of magnetic fields and their profound effect on planets and their potential to harbor life. The field of studying signals from other galaxies has grown rapidly over the past few years. For example, the giant Metro-Wave Telescope in India has detected a faint signal from the most distant galaxy to date. The signal detected by YZ Ceti opened another new window into the universe, reminding us of how much we still have to learn about our world. As we look to the future, the study of signals from other galaxies will continue to be the focus of space research. Each signal carries the potential for new discoveries. So when we look up at the night sky, let's remember that we're not just looking at stars and galaxies. We're looking at a universe filled with unseen forces, whispered signals, and hidden possibilities.